Thank you very much. I keep forgetting about that, Curtis. I don't know why. Sometimes I look back, I watch back the recording, and I'm like, geez, I look like such a retard here. Anyways, I shouldn't use that word. That's bad. Sorry, apologize. And I recorded it. Okay, so let me go back to this screen share. Now, water hardness. Now, we use the term hardness of water. Right here, we use the term hardness to designate the amount of dissolved minerals. And there's three types that we want to really be concerned about when we're talking about this. Temporary hardness. And temporary hardness is these bicarbonates of calcium and magnesium, and it calls temporary hardness. So, you know, when this comes out, when water is heated, it settles out as scale. And right at that temperature of 140 degrees, what do we set our hot water tanks to? 140 degrees, okay? So tanks become coated at higher temperatures. The higher the temperature, you would get that temporary hardness coming out of the water settling as scale. And sometimes it's a white kind of bicarbonates of calcium and magnesium. It's a white kind of flaky stuff. You could see it on outlets of taps sometimes, on the aerators, that sort of thing. That's exactly what that stuff is. Then there's permanent hardness. And this really is that sludge, right? Listen, some water in southern Alberta is pretty darn bad. It is awful, awful stuff. And quite frankly, some of it we have total hardness, and some of it is unfit for human consumption unless we treat it. So those are the three types of hardness of water that they talk about in this ILM. Water treatment is big business in southern Alberta, huge business. So if you are ever in a niche kind of way and you get into that, I mean, there's a lot of people that want it, need it, love it. Listen, it's a good business to get into, okay? As a plumber gas fitter, it is something good. What's next? Now we have this classification, and this is how much hardness per 50 milligrams per liter. And you know, that's just a scale. It's right out of the book. But here's something that I really want you to see is this. Now this sheet that I have here that I'm showing you, I have put it in D2L under the buoyancy under handouts. So you do have this sheet. It is there, so you could have that. So I'm gonna stop sharing that. Awesome. Do you have any questions so far? Any questions? No? Okay.
Hey, Doug.
Yes, sir.
At the beginning, you said water is the most abundant
compound. The most abundant compound.
What's abundant?
Lots. We have more of it than anything.
Oh.
It's the largest amount of compound we have on this earth.
Okay.
Okay.
Good, thank you.
Yeah. I'm going to go back to the ILM. And here it is here. So they talked about total hardness. There's that table right out of the ILM. So they talk about hot water tank thermostats must not be set greater than 140, because then we get a lot of something going on inside and it reduces the heat transfer capabilities. Permanent hardness, effects of temperature on hot water heating systems. Now, this is also important because we deal with this stuff all the time. And it goes on to say that, man, it'll always happen. So our boilers here in Southern Alberta need to be serviced, need to be maintained. They're not going to run forever without any problems. They are going to get coated with this stuff all the time. And heat accelerates the process. Okay, so temperature also affects the solubility of chemicals in water. Okay, so that's what that is. Now, we also talked about water expanding. I remember we talked about water expanding as it goes from the most dense at 4 degrees C all the way to the boiling point. It expands. And again, we need to have protection from overrise pressure due to high temperatures. Okay. And how do we protect? So this statement right here, it says a hot water tank must be protected from overpressuring due to high temperatures. How do we protect a hot water tank from that? Does anybody know?
Pressure relief valve.
TP, yes, right, with temperature pressure relief valve. So that is absolutely correct. So that's why they're there. It's for protection of property. And look at that, we're getting to objective 2 now for buoyancy. Okay. So we're going to talk about the 3 laws of buoyancy and describe the effects of buoyancy on regular shaped objects submersed in water or submersed in a fluid. But the first thing we're going to do is we're going to watch a short video. Okay, I'm going to see if I can get us to watch a short video. I hopefully got this queued up. Does everybody see my screen there? It says great educators.
Yep.
Yep.
Okay, now you may have to click on it so you have more of a spotlight view, so it's going to be big in your screen. So we're going to watch this. It's short, it's 3 minutes long, and we're going to watch this video from one of our friends here, Archimedes.
Does anybody have any volume on that?
Yeah, I can't hear.
I got no sound.
Yeah, no sound.
Hey Doug, we got no sound.
Oh, okay, hang on. Hang on. You have no sound?
Nope.
We couldn't hear it.
You can't hear it. Okay, hang on a second. It's the first time I've ever actually did a video on this thing. So let's see. Let me scroll back to this.
I think you have to click the optimize video and share my screen computer sound. Once you click the share button, it should come up on your small box in the left bottom corner of that box.
On the left?
Bottom, left
Yeah.
bottom.
Leave computer sound? No. Audio settings, I got it there.
No, once you press the share screen button,
Yeah.
it should come up on your left bottom.
Oh, share computer sound.
And probably you might want to click the optimize video, the screen, I guess.
Okay, excellent.
It's more smoother.
Okay, let's try that again. Awesome, thank you for that.
Yeah, it's working now.
Perfect.
Some of the best opportunities to learn are the moments in which we are perplexed, those moments in which you begin to wonder and question. These moments have happened throughout history and have led to some truly amazing discoveries. Take this story, for example. There once was a fellow named Archimedes. He was born in 287 BC in the city of Syracuse in Sicily. He was a Greek mathematician, physicist, engineer, inventor, and astronomer. One day, Archimedes was summoned by the king of Sicily to investigate if he had been cheated by a goldsmith. The king said he had given a goldsmith the exact amount of gold needed to make a crown. However, when the crown was ready, the king suspected that the goldsmith cheated and slipped some silver into the crown, keeping some of the gold for himself. The king asked Archimedes to solve the problem, but there was a catch. He couldn't do any damage to the crown. One day, while taking his bath, Archimedes noticed that the water level in the bathtub rose and overflowed as he immersed himself into the tub. He suddenly realized that how much water was displaced depended on how much of his body was immersed. This discovery excited him so much that he jumped out of the tub and ran through the streets naked, shouting, "Eureka!" which comes from the ancient Greek meaning, "I've found it!" What did he find? Well, he found a way to solve the king's problem. You see, Archimedes needed to check the crown's density to see if it was the same as the density of pure gold. Density is a measure of an object's mass divided by its volume. Pure gold is very dense, while silver is less dense. So if there was silver in the crown, it would be less dense than if it were made of pure gold. But no matter what it was made of, the crown would be the same shape, which means the same volume. So if Archimedes could measure the mass of the crown first and then measure its volume, he could find out how dense it was. But it is not easy to measure a crown's volume. It has an irregular shape that's different from a simple box or ball. You can't measure its sides and multiply like you might for other shapes. The solution, Archimedes realized, was to give the crown a bath. By placing it in water and seeing how much water was displaced, he could measure the volume. Then he'd calculate the density of the crown. If the crown was less dense than pure gold, then the goldsmith most definitely cheated the king. When Archimedes went back to the king and did his test, the story says, he found that the goldsmith had indeed cheated the king and slipped some silver in. These days, using the way an object displaces water to measure volume is called Archimedes' principle. The next time you take a bath, you can see Archimedes' principle in action. And maybe you'll have a genius idea of your own.
All right. Well, that guy is pretty smart, that Archimedes guy. Now, here's the thing about Archimedes. He, like I said, he's using density, mass, and volume to figure something out. So what we are going to do is we are going to do some density questions together. We're going to do some relative density questions together, and then we're going to talk about buoyancy, and then we're going to figure out how to use Archimedes' principle to solve for volume and that sort of thing. Okay, so we're going to do some math. We're going to do it on, I got some paper here. I'm going to throw some questions up. So if you get yourself some paper, pen, pencil, calculator is important, and we will do that shortly. But first, we're going to take a break. Okay, we're going to get you guys to go get hydrated, all that kind of stuff, stretch your legs. So let's come back here at 9 o'clock, and we will start the lesson, and we're going to do density, specific gravity, buoyant force, and we're going to solve for all kinds of weird things, and we're not going to solve any world problems, but we're going to be a little smarter after. How's that? Good? Everybody good?
Good.
Okay, so take yourself a break. Come back, 9 o'clock.
Doug, I have a question about raw.
Sure, what's up?
Oh, sorry. Water softeners, does that go through everything? Water, first toilets, sinks? I'm asking about drinking water, if the water softener goes in the drinking water, I guess.
Okay, I understand. No, we don't want to drink softened water. It's not that great. It's kind of gross. So when you're piping these softeners in, and if it's after the house has been built, then basically you just run it for the cold line going into your hot water tank, most always. We don't want softened water out to our hose bibs. We don't want it to our toilets. Why? Because you're just flushing down softened water, right? So we don't want it on our kitchen sinks where we get most of our drinking water, but we want it on our hot for our dishwasher. We want it on our hot for our laundry. We want it on our hot for showers, right? That sort of thing. Okay.
So only when it comes in the hot water.
Yeah, if it's an aftermarket or an older house that you're putting it in, you're typically just putting it on the hot water or the cold inlet for the hot water tank.
Okay.
So you have softened hot water. Unless you want to really be able to pair out all of the other things. It works great to put a home run system in, and then you could soften the water where you need it, right?
Yeah.
It's one of those things. Yeah.
Okay. Thank you very much, Doug.
No, you're welcome. Okay, let's take a break. Well, hopefully everybody gets back here in a few minutes. Hello, everybody. Is everybody back yet? Everybody back?
Back.
Almost. Let's get back to it. Okay, so to start off, we have the density triangle, and this is to calculate density. So I wrote down a couple things here. Mass, what mass is? Mass is always going to be in pounds or kilograms. Our volume is typically going to be in cubic feet or cubic meters. I know I put cubic inches there, but mostly it's cubic feet and cubic meters that we want to be concerned about when we're going to do any kind of buoyant force calculations or etc. Density, the D is density. I didn't write out that that's density. It's mass per unit of volume. And now those standards that we're going to use today is the density of water, which is 62.4 mass per unit of volume, pounds per cubic foot, or metrically 1,000 kilograms per cubic meter. Now we're going to then, if we take this next one here, we have the density of the object and if we take the density of water, that would give us the relative density. So that's another formula triangle. So when we take the density of the object divided by the density of water, and this is the standards right here. So these are these numbers that go there, the standards, will give us the relative density. Now, here's the first question I'm going to write down that we're going to do together. We have 900 pounds block. Weighs 900 pounds. It has a volume of 5 cubic feet, that block. What is the density of that block? Well, we take our mass divided by the volume will equal the density. So 900 divided by 5, the density of this block is 180 pounds per cubic foot. Yes? Perfect. Now to find the relative density of that block is we simply take the density of the object right up here divided by the density of the standard. So we will divide that by 62.4 pounds per cubic foot, and that will give us the relative density of that object, which happens to be 2.88 is the RD. And what that means is that it is 2.88 times heavier than water, fresh water, I should say. Okay. So that's not bad. That's pretty easy. Did everybody kind of understand that? Okay, because I'm going to do another question here. I'll leave that up for a half a minute, and we're going to do a couple more questions. So I'm just going to transfer some information here. So we have that 900-pound block with a volume of 5 cubic feet with a density of 180 pounds per cubic foot, and we had the relative density of 2.88 times heavier. Okay, so those are our standards right there. Now, because when you immerse an object in water. Okay, when you put that object in water, so this block, I'm going to draw a picture of a block. This weighs 900 pounds. Okay, and if I take that and I put it in the water, now we know it's heavier than water. It will sink, right? But listen, it's not going to weigh 900 pounds when it's in the water. This is the only way I could sweep my girlfriend off her feet, is in the swimming pool. There's no other way, right? I can't, she just weighs too much. I can't carry her around. So the only way I could do it is in the water, because when an object is submersed in a fluid, it will have a certain amount of what we call buoyant force pushing up on that object. That's why when things are in water, they don't weigh as much. There's a buoyant force pushing up on that. Now that buoyant force is directly related to the volume of the object. Buoyant force, let me write that down. The buoyant force is directly related to the volume of the object. Now we could do this a couple of different ways. We could use the volume to calculate the buoyant force, which I will do. So if I had 5 cubic feet and I multiplied that by, so if I had an object that was 1 cubic foot and I put that 1 cubic foot object in there, it will displace 1 cubic foot of water. That 1 cubic foot object will displace 1 cubic foot of water. And we know 1 cubic foot of water weighs how much? Weighs 62.4 pounds. So the buoyant force pushing up on this object is 312 pounds. Meaning this 5 cubic foot object, this is 5 cubic foot, has a buoyant force pushing up on it on 312 pounds. So the object in air weighs 900 pounds. The buoyant force is 312 pounds. So when this object is in the water, it only weighs 588 pounds. So the object, when that 5 cubic foot object in the water only weighs 588 pounds, because we have a buoyant force of 312 pounds pushing up on it. So that's kind of cool. So let me just try something different with the same parameters. So if I had an object that weighed 900 pounds in air, meaning out here in air, and it weighs 588 pounds in water, I'm going to ask you, what would the buoyant force be? Well, buoyant force can also be calculated by taking the object mass in air and minusing object mass in water will equal the buoyant force. So 900 minus 588, the buoyant force for this object is 312 pounds. So that's another way of calculating buoyant force. The other way for calculating buoyant force is taking the object's volume and dividing it by the standard density of water will equal the buoyant force pushing up on that object. Let's do another one. Does everybody have that down before I move it? Just yell at me if I'm going too fast, okay? Please. Give me a shout if I'm going too fast.
So 588 is the mass in water, right?
That's correct. That's the mass or the weight of the object when it's in the fluid. Yes.
And to get that, you just take the volume and the times by the density of the water, right?
Yeah, right there. Absolutely. Okay, so now we're gonna do another one here. So an object has a volume of 9 cubic meters. And it weighs 1,700 kilograms. So I want a couple of questions answered. For this one, I want to know A, the density. B, I want to know the relative density. C, I want to know the buoyant force. And then D, I want to know, will it float or sink? Okay, so I have an object, 9 cubic meters, weighs 1,700 kilograms, and I want to know all these answers from that information. So the first thing I do, I have my density triangle, mass, volume, density. So I can find the density by taking the mass, dividing it by my density, or my volume, excuse me, will give me my density. And if I do that math quickly in my head, so the density is 188.88 kilograms per cubic meter. Pretty straightforward. Now I want to know the relative density. So I'm going to take my density and I'll divide it by the standard. The standard is 1,000 kilograms per cubic meter. That's the density of water. Relative density is 0.1888. Now, I want to calculate the buoyant force. I said in the last picture that the buoyant force is directly related to the volume of the object. I have 9 cubic meters. So the buoyant force pushing up on this object has to be multiplied by the standard. It has a buoyant force of 9,000 kilograms. So that object weighs 1,700 kilograms. So I'm going to submerge this object in the water, and it has a buoyant force of 9,000 kg, but it only weighs 1,700 kg. Is it going to sink or float?
That's gonna float.
It's going to float. And one of the biggest indicators if it's going to float, if this relative density is less than 1, object will float. Always float if it has a relative density of less than 1.
How did you know to times the 9 by 1,000 instead of dividing? Like,
Okay, well, that's a great question. Because the object has a volume of 9 cubic meters, I'm always going to multiply to find the buoyant force. I believe we wrote that down. Oh, it's a times. I think I put divide there last time. Times. Yeah, we multiply. We multiply to get the buoyant force. Okay, that's how we do it.
so to find the force, it's object volume times standard density, or
Standard,
never
the
mind.
standard density of the fluid it's in. So we're
Okay.
talking about fresh water. Okay.
Okay.
Yeah. Okay. So let's do another question.
Sorry, Doug. The mass in the air minus the mass in water, is that that's not the buoyant force, is it?
No, it's the buoyant force would be the mass of the object in air minus what the mass of the object would be in water. So this thing weighs absolutely nothing when it's in water. It weighs 0. This 1,700 kilogram object, because it has such a big volume, it will weigh absolutely nothing. I could move that around by myself in a swimming pool, that 9 cubic meter object, because it doesn't weigh anything, just big. Hopefully that answers your question. So
Just go back one page from that. I wrote something down. I think I wrote it down wrong.
okay. That one?
Yeah, that's the one.
Hey, Doug.
Yes, Kurt.
Would atmospheric pressure have anything to do with this?
We are working at standard temperature and pressure. How's that? So no, we're not really quantifying the air pressure or anything like that. Okay.
Okay, thanks.
You got that one? Can I move it?
Yeah, go ahead. Yeah, thank you.
Okay. So there we got that one. Now I'll try to quantify this a little bit. So we have boats that floats on water, yes? Happy boat sailing along. Now it's because the volume is very large on these boats, okay? A lot of that volume on these boats is made up of air, quite frankly, so that's still a large volume, giving them massive amounts of buoyant force. Like you could have entire hotels floating on the water because the volume of those big boats are so big that it has an incredible amount of buoyant force because of its volume. Now, I don't want to bust any real scientific things, but does anybody know why boats in the Bermuda Triangle sink so fast? Secrets revealed right here.
Gas coming out.
The Wicked
It
Witch of the
is.
West.
So on the bottom of the ocean here, what happens is you have gases bubbling up, and you have at times massive amounts of gases bubbling up in this area out of the ocean floor. Methane, carbon dioxide, all that kind of gases just start to bubble up from the ocean floor like a mini volcano almost. And what kind of buoyant force do you have in air? Have you ever tried to float in air? No. So if you go over a big pocket of air bubbles or even methane bubbles, you have no more buoyant force. You cannot float in air. And what happens is your boat sinks really fast because it's like having a boat trying to float in air. You know what that does? It goes right to the bottom. It crashes fast. And so them boats have no more buoyant force and they sink right to the bottom of the ocean. So that's the Bermuda Triangle solved, man, right there. Right? Any questions? No? Hopefully I'm not confusing you too much. But what about planes? What about the planes? How do the planes all crash? Anybody know?
Pressure differential?
No, it's pretty much aliens. That's why.
Okay.
I'm only kidding. I don't know why planes go down.
Waste of gases and stuff in the air choke out the engine.
Maybe. That's a good question, right? Maybe they catch on fire. I don't know. Anyways, let's do another example. And what I'm going to do here is I'm going to write out this question. I want you guys to write out this question. And then I'm going to break you off into some rooms, and then you figure out all of these things. So let me write down. So I want to know the volume. B, I want to know the density. C, I want to know the relative density. D, somebody's trying to call me. But, D, where am I here? I want to know the buoyant force. Boy, that's annoying. On E, I want to know if it sinks or floats. Now, here's the question. Okay, so there's the parameters of the question. I want you to take some time and solve that. Write that down, please. And then, okay, you ready? Here we go. You guys are all in your rooms together. Here we go. Please join the breakout room.
Yeah, hold on. Can you just let me see that question again? I'm still writing it down.
Sure. What's that?
Do you mind letting me see that question again? I was still writing it down.
Sure.
Okay, thank you.
You're welcome. Jake, pick one room. I know you're kind of.
Yeah, I'm using my phone and it locked me out of the one room when I tried to go in there though, so I just signed back on.
Okay, yeah, I got you 3 times now.
My bad.
It's okay. I mean, you know what? You're trying your best, and that's good. I appreciate that. Can you get in one of those rooms? Here, let me assign you.
Give me the option here.
Let me see what I can do here. I'm going to assign you to a room. Here we go. There. Try that.
Inches.
And a length of 13 feet.
Oh, gotcha.
All right. You guys are doing good. Keep it going.
So far, yeah.
Yeah. Okay. So when you guys are in this room, I would ask you to unmute your cameras so you can see each other. And I know you're working on it together, but just unmute your cameras the best of your ability and try to, communicate. Okay.
Hey, Doug, you're muted.
Thank you. So when you're in these meetings, I'd like you to show your camera at least with each other. And so you can see each other and talk to each other in a real way, so to speak. Okay, awesome. Thanks.
That's
Hi, guys. So you're only on 3 of you working together, so hopefully that's okay. You guys can figure it out.
yeah. Yeah, we're just a little stuck on finding our density with cylindrical shape. That's where we're getting stuck.
Okay, it's a cylinder. How's that? The
Yeah.
volume of a cylinder.
Volume of a cylinder, perfect.
Right.
The formula sheet We're gonna pull that up.
So that's pi r squared height.
Height.
Yeah. Okay, I got it. Fuck,
Keep
that's
working.
easy. Shit.
All right. Okay, guys, I want you to just unmute your cameras so everybody can see everybody as you guys work together. I know Brandon and Andre is, but Matt and Frankie, you want to unmute your camera so you can see each other, work together on this? Yes?
Yeah.
Beauty.
Yeah.
Okay, keep working. Well, hi, everybody. I'd like you to unmute your cameras while you're in a breakout room. So you're face to face with people as you're working together on this stuff. Okay, so then you know each other a little bit. All right, awesome. Thank you. How you making out? Everybody got this?
Getting there.
Yeah, okay, good. Good.
Yeah.
Okay, I'll leave you alone for a few minutes.
So